Assalamualaikum and hi, my name is Kuzaima Rabia binti Muhammad Karonizar. My metric number is DE190155. Today I would like to explain about part A. There are two questions. Firstly, it asks us to differentiate PI, PD and PID controllers. This is the table that contains four types of controllers, which are P, PI, PD and PID. P is proportional, I is integral, and D is derivative. P controller is a form of linear feedback control, while PI is a form of feedback control. PD is a combination of feed-forward and feedback control, and PID is a combination of all three types of control. We can see here the advantages and disadvantages. However, the most obvious features or aspect that we can see that become the difference between all these type of controllers is response time, gain, transient response, offset, steady state error, and stability. In the same question, it asks us to explain which one is suitable to zero steady state error to the step reference input. And all these controllers have their own pros and cons. However, the most suitable for zero steady state error is a PID controller because the transient response is acceptance and the system is also stable. Next, for the second question, the instruction asks us to study and understand the different classical tuning method, which are trial and error method and also Ziegler-Nichols method. And we have to list out their similarities and difference. Generally, trial and error method is based on guess and check, while for the Ziegler-Nichols method, it is frequently used when the mathematical model of the system is unavailable. This is the table for the similarities and differences between these two types of methods. We can say that both methods is used for open and closed loop systems, and it will cause the unstable system. While for trial and error method, the main controller is proportional, and Ziegler-Nichols is there's no main controller. Time consumed and accuracy for trial and error method is decreased, while for Ziegler-Nichols method, it is increased.
And hi, my name is Nur Akila binti Saidun. My metric number is DE190044. So today I will explain about the pre-lab activities for part B. So first of all, we have to go to the PID controller tuning at the Simulink. And for the question 1, we have to change the speeds reference. But for now, we run this simulation first. And we will get this graph. And after that, we change the speed reference to 2000, and 3000. And then we click OK and we run. And after we run, we will get this graph. The second question is we have to analyze the engine speed RPM when the PID parameter are used in different. So we can go to the PID controller, and here I have set the parameter of the PID controller to proportional 10, integral 10, and derivative 10. So we click OK and we can run this simulation. And this is the graph for the parameter that I have changed. Because we want to look the different parameter from the PID, so we can change the PID parameter to 0.5, 0.05, 0.10, and click OK, and after that we can run the simulation and we can identify the graph. So here the graph for the new parameter that I have key in. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Indonesia Camilla Shukri, metric card number DE190115. So for the experimental setup, what and how the data will be acquired. So first, to obtain the data, we need to make a simulation drawing block diagram with the MATLAB. This analysis will be conducted by using different parameters of PID in each block diagram. So, and then open the PID tuner application and creates an initial controller to compute a linear plant model from the Simulink model. Manually set design criteria into design modes to tune the controller. This is to calculate the PID settings to ensure the system is stable. Fourth, re-import the developed controller setting into PID controller block and verify the controller's performance in Simulink. So to see the controller parameters, that is P and I, as well as the performance of the measures, click Show Parameters. What and how the analysis will be conducted. So for this lab, we are required to do a virtual laboratory that we work on the lab experiment at our respective homes. We are required to use a software tool which are Simulink and MATLAB that can simulate different types of block diagram system. So by using Simulink, we will draw a model into a blank window and save the files into MATLAB command prompt. And by referring to the instructions, a design is required to study the effects of parameters. The parameters involved in the studies are types of controllers that are PID, PI, PD, P and I. Next, the parameters of time domains are continuous and discrete. Lastly, signal tracking for smooth control transfer and multi-loop control will enable the tracking mode parameters.
Assalamualaikum, my name is Nur Aina binti Johari, JA190111. So I will cover the MOM part, which is 1.4 to 1.5. So for the 1.4, what are the expected results? So I make the table. For the rise time, when we increase the proportional gain, the rise time will decrease. When we increase the integral gain, the rise time will decrease also. When we increase the derivative, rise time will have a small changes. And for the overshoot, when we increase the proportional or integrator, the overshoot will increase. When we increase the derivative gain, the overshoot will decrease. So for the settling time, when we increase the integral gain, the settling time will increase. And when we increase the derivative gain, the settling time will decrease. Okay, so when we increase the proportional, the steady state error will decrease. When we increase the integrator, the steady state error will be eliminate the error. When we increase the derivative, SSE will have a small changes. So next, for the 1.5 block diagram using Simulink. So this is the block diagram for this experiment. So I choose to show the PID block diagram from the Simulink.
Hi and Assalamualaikum. My name is Nora Shikin binti Nasaruddin. My matrix number is DE190039. I will explain the question part 2 PID control experiment using trial and error. For question 2.1, tabulate the desired output. For start time is 2, initial value is 2000, desired RPM 3000, and settling time less than 5. And this is a block diagram to set the desired output. Start time is 2, initial value is 2000, final value is 3000, and sample time is 0. First trial for P controller, set P equal to 10. And this is the output for P controller first trial. Rise time 312.903 millisecond, overshoot 13.068%. For 2N trial, we need to set P 0.02 and this is the output graph for P controller 2N trial. Rise time 203.540 millisecond, overshoot 14.44%. For PI controller first trial, we need to set P equal to 0.02, I equal 0. And this is the output graph for first trial for PI controller. The rise time 295.683 millisecond, overshoot 99%. For 2N trial, P equal to 0.02, I integral equal to also 0.02. And this is the output graph for PI controller for 2N trial. The rise time 331.321 millisecond, overshoot 14.368%. For PID controller, for PD controller, we need to set the proportional P equal to 0.02 and derivative is 0.05. And this is the output graph for PD controller first trial. For PD controller 2N trial, we need to set the proportional P equal to 0.02 and derivative D equal 0.002. And this is the output graph for 2N trial PD controller. The rise time for 18.560 millisecond, overshoot 0.515%. For PID controller, for first trial, we need to set the proportional P equal to 0.02, integral I equal to 0.2, and the derivative is 0.005. And this is the output graph for first trial PID controller. The rise time is 109.384 millisecond, overshoot 259.59%. For 2N trial, we need to set proportional 0.02, integral 0.002, derivative 0.005. And this is the output graph for 2N trial PID controller. The rise time 900.5415 millisecond, overshoot negative 0.727%. That's all, thank you.
5. So to summarize all the results, part 2.1 until 2.5 summarized all the results in a suitable table, which is like this. So we can see here the setting time is the same because we use 1.5 seconds, and then for controller B The response time was a bit later than other controller, which is 6.5, and the maximum overshoot is the least among all the other controllers, which is 13.068%, and the steady state response is also the least among all other controllers, which is 1.017. It has the highest maximum overshoot, which is 99.01%, and also 9.702 steady state response. But on the other hand, PID has the highest steady state response, which is 9.809. To compare all the results we got during this experiment, the proportional gain is increased by using Ziegler-Nichols method formula in a PID controller that is by utilizing trial and error. The closed loop actions are required by PID controllers to maintain the output between the process variables, and to control the steady state error, the PID controller must reduce the system settling time. The derivative gain must be higher than theoretical. Hence, the outcome matches the predicted results that we discussed before.